welcome to the Deep Dive. Today we're diving into the world of oil and gas production, specifically hydraulic fracturing.
Yeah?
We're going to be looking at treatment scheduling.
Okay.
That's how engineers decide how much fluid and proppant
Right?
to use during a fracturing operation.
Yeah.
You're interested in maximizing the effectiveness of these treatments,
Yay.
and understanding the strategy behind them is key.
Yeah, that's right. It's like a recipe
Okay.
where the ingredients are fluids and proppants and the instructions are the treatment schedule.
Got it.
Get it wrong and your well might not produce as much as it could.
Okay, so let's start with those ingredients.
Okay.
Our sources mentioned perfect support fluids.
Yeah.
Are these as amazing as they sound?
Well, perfect might be a bit of an exaggeration,
Okay.
but they are pretty remarkable. These fluids like cross-linked gels, foams, and emulsions are incredibly viscous,
Okay.
which means they're thick and gooey, almost like honey.
Oh, wow.
This viscosity is crucial because it allows them to carry the proppant, the sand-like material that keeps the fractures open, deep into the rock formation.
So it's not just about pumping fluids down there.
Right.
It's about making sure the proppant reaches the right spot.
Exactly. The ideal scenario is for the proppant to reach the very tip of the fracture, just as the initial pad fluid.
Okay.
The stuff that opens the fracture in the first place depletes. This creates a uniformly propped fracture, maximizing its conductivity,
Okay.
which is basically how easily oil and gas can flow through it.
That makes sense, like making sure every nook and cranny of the fracture is propped open.
Right.
But how do they figure out exactly how much pad fluid to use?
It's a delicate balance.
Yeah.
You need enough to create and extend the fracture
Yeah.
to the desired length, but not so much that there's no room left for the proppant.
Right.
It involves a complex calculation that takes into account things like fluid loss into the surrounding rock, the shape of the fracture, and the properties of the formation itself.
So there's a lot of science and math involved, even before the actual fracturing even begins.
Lots of it.
Our sources mentioned that even with perfect support fluids, things don't always go according to plan.
Unfortunately, that's true. Even with the best laid plans, we have to contend with the forces of nature. One challenge is gravity segregation, where heavier proppant particles tend to settle faster than lighter ones. Another is viscous fingering, where the proppant-laden fluid doesn't flow evenly, creating channels and gaps in the proppant pack.
So it's like trying to control a very messy river.
It's a good analogy.
And what about the concentration of proppants in these fluids?
Yeah.
How much is considered the sweet spot?
A common recommendation is a final proppant concentration of 8 pounds per gallon, or 8 ppg.
Right.
This concentration seems to strike a good balance between conductivity and coverage.
Okay.
Too little proppant and you won't get good conductivity.
Yeah.
Too much, and you risk clogging the fracture or wasting proppant.
8 ppg. Got it.
Yeah.
Sounds like a delicate balance to achieve.
It is.
Is there a visual I could check out to get a clearer picture of how this all works?
Absolutely. If you look at figure 7.1 in the source material, you'll see a great illustration of perfect support fluids in action. It really helps to visualize the process.
Perfect. I'll definitely take a look at that. So we've talked about the ideal scenario with these perfect support fluids.
Right.
But what about situations where a simpler, more cost-effective approach is needed?
Yeah.
That's where banking fluids come in, right?
Yeah, exactly. Banking fluids are a bit less sophisticated, but still effective in many situations. Instead of relying on perfect proppant transport, they leverage gravity and proppant settling to create a high conductivity pathway near the wellbore.
So instead of trying to get the proppant all the way to the fracture tip, you're letting it build up closer to the well.
Precisely. As the proppant-laden fluid flows into the fracture, the proppant particles naturally start to settle near the wellbore, forming what's called a proppant bank.
Interesting. What are the advantages of this approach? It sounds almost too simple.
Well, simplicity is a major advantage. Banking fluids use simpler, less expensive base fluids that don't require complex additives. This makes them more cost-effective than those fancy perfect support fluids.
That makes sense, especially if you're working with a tight budget. What other benefits are there?
They're generally easier to manage, reduce the risk of proppant pack damage, and can even help control the height of the fracture, which can be important for preventing unwanted communication with nearby zones.
So while it might not be as precise as perfect support fluids, it has its own set of advantages.
Right.
But there must be some downsides to consider, right?
Of course.
Yeah.
One potential issue is that because the proppant isn't evenly distributed throughout the fracture, the effects of gel residue from the fluid can be more pronounced near the wellbore, potentially hindering flow.
So it's a trade-off between simplicity and potential drawbacks.
Yeah, you could say that.
Are there any other surprising things about how banking fluids work?
Yes. One common misconception is that you can boost conductivity at the end of a treatment by tailing in with a higher conductivity proppant.
Okay.
But it turns out this isn't as effective as one might think.
Really? Why not? I would think adding a better proppant at the end would be beneficial.
It all comes down to where the proppant ends up. Remember, with banking fluids, the proppant settles near the wellbore, and the last proppant injected ends up furthest from the wellbore. So that high conductivity proppant you add at the end might not even make it to the most critical part of the fracture, which is near the wellbore where the oil and gas are flowing in.
Ah, I see. Placement is everything.
Yes, it is.
So you're saying that even though it sounds good in theory, the reality of proppant settling makes it less effective.
That's right.
Is there a visual that helps illustrate this banking fluid process?
Yes. Figure 7.4 in the source material does a great job of showing how proppant banking works.
Okay.
It's worth taking a look at.
Excellent. I'll add that to my list. So far, we've covered two main approaches to treatment scheduling: perfect support fluids and banking fluids.
Right.
But our sources also mention a third technique called tip screen-out fracturing, or TSO.
Yeah.
That sounds pretty intense, almost like something went wrong.
It does sound a bit alarming, doesn't it?
Yeah.
But TSO fracturing is actually a deliberate technique used to increase propped fracture width, which is especially important in high permeability formations.
So it's for situations where you need a wider pathway for the oil and gas to flow.
That's right.
How does intentionally creating a screen out help with that?
It's a bit counterintuitive, but here's how it works.
Okay.
In TSO fracturing, we intentionally create a blockage or screen out at the tip of the fracture using proppant. This halts the fracture's length growth.
Okay.
But here's the key. Pumping continues, and that continued pumping combined with the blockage forces the fracture to widen instead of extending further.
So instead of letting the fracture grow longer, you're forcing the pressure to push the fracture walls apart. It's like inflating a balloon. At some point, it stops getting longer and just gets wider.
A perfect analogy.
But why is width so important, especially in those high permeability formations?
That's a great question. In high permeability formations, width is crucial because of turbulent flow.
Okay.
Think of a narrow, fast-flowing river.
Yeah.
It's chaotic and turbulent,
Okay.
but a wider river with the same amount of water flowing through it will be much calmer and smoother. The same principle applies to fractures. A wider fracture reduces turbulence and allows for more efficient flow of oil and gas.
That makes sense.
Right.
It's all about maximizing that flow rate.
Right.
So this TSO technique, where did it come from? It sounds like a risky maneuver.
Believe it or not, it was inspired by an undesirable event, a screen out, that happened in a low permeability gas well.
Interesting.
You can actually see the pressure data from that event in figure 7.5 of the source material.
Fascinating.
Yeah.
So what was initially considered a problem turned out to be a valuable insight.
It did.
What does the proppant schedule look like for a TSO treatment?
It usually involves a two-stage process.
Yeah.
First, you have the pin stage, where you pump in low proppant concentrations to intentionally create that blockage at the fracture tip.
Yeah.
Then you have the fill stage, where you pack the widened fracture with higher proppant concentrations to ensure conductivity.
So it's a delicate balance between controlling the fracture's growth and then filling it effectively.
It is.
Is there a visual that helps illustrate the difference between a normal proppant schedule and a TSO one?
Absolutely.
Yeah.
Figure 7.16 in the source material compares the two, and you can see the distinct difference in how the proppant is distributed.
Great. I'll be sure to check that out.
Yeah.
We've now covered three distinct approaches to treatment scheduling: perfect support fluids, banking fluids, and TSO.
Right.
It seems like a lot can go wrong even with careful planning.
It can.
Are there any other gotchas to watch out for?
Unfortunately, yes. Even with the most meticulous plans, unexpected issues can arise. One particularly tricky challenge is something called pressure-dependent leak-off, or PDL.
PDL. That doesn't sound good. What exactly is that?
Imagine you're pumping fluid into the fracture and everything seems to be going smoothly.
Okay.
But then as the pressure increases, it can suddenly trigger the opening of natural fissures or cracks in the rock formation surrounding the fracture.
Oh, I see. So it's like accidentally opening up a leak in a water pipe.
Exactly. These fissures act like escape routes for the fracturing fluid, leading to a sudden and potentially significant fluid loss.
That sounds like a real headache. How does this unexpected fluid loss affect the whole operation?
It can be a major problem. This rapid fluid loss can cause the proppant-laden fluid to dehydrate, prematurely turning it into a thick, immovable sludge.
Oh, no.
And if this happens near the wellbore,
Right.
it can lead to a sudden and complete blockage known as a premature screen out.
So instead of creating a pathway for oil and gas to flow, you've accidentally created a roadblock.
It is a bit like that.
That's definitely not ideal.
Definitely not.
And what makes it even more challenging is that these surprises are often triggered by the higher net pressures used in the main treatment.
Right.
Compared to the initial mini-frac test.
Yeah.
Which is used to characterize the formation.
Right.
So even though you might think you have a good understanding of the formation based on the mini-frac, things can change dramatically when you ramp up the pressure for the main treatment.
Precisely. The higher pressures can cause the fracture to behave differently, leading to these unexpected fluid losses and potential screenouts.
Okay.
And that's why understanding and anticipating potential issues like PDL is crucial for successful treatment design.
Right.
It's not just about planning for the ideal scenario, it's also about mitigating the risks of the unexpected.
It sounds like a constant balancing act, juggling all these factors to achieve the best outcome.
Well,
We've covered a lot of ground in this first part of our deep dive into hydraulic fracturing treatment scheduling.
we have, but there's still lots more to discuss.
Welcome back to our deep dive into hydraulic fracturing treatment scheduling. It's amazing how much goes into planning these operations, from those specialized fluids to dealing with unexpected challenges like pressure-dependent leak-off.
It's a testament to the ingenuity of engineers who've really pushed the boundaries of what's possible in accessing these valuable resources.
Absolutely. And speaking of pushing boundaries, we've got to talk about proppant.
Yes.
It's more than just sand.
Yeah.
What are the key things that make a good proppant?
You're right. Proppant is a critical part of the equation, and it's not just any old sand that will do. We need proppant that can withstand incredible pressure, thousands of feet underground, but also allow oil and gas to flow through it easily.
So it needs to be tough but porous, like a microscopic version of those sturdy sponges you use for heavy-duty cleaning.
I like that analogy. And the ideal proppant can vary depending on the formation. The type of rock, the depth of the well, and the expected production rates all factor into selecting the best material.
So it's not a one-size-fits-all situation.
Right.
What are some of the options?
Yep.
Our sources mention different sizes and strengths.
Size is definitely important. We use a mesh scale to describe proppant size,
Right.
with smaller mesh numbers indicating larger grains.
Okay.
A common range is from 12-20 mesh, which is fairly coarse, to 40-70 mesh, which is much finer.
And how about strength? What are these proppants made of that allows them to withstand such extreme conditions?
For shallower wells with lower pressures, naturally occurring sand can be a good choice. It's cost-effective and readily available.
Right.
But for deeper, higher pressure environments, we often need something more robust.
Something that won't crumble under pressure, so to speak. What are those tougher options?
Engineered proppants are a game changer in these situations.
Okay.
Resin-coated sand is one option.
Yeah.
It's basically regular sand with a resin coating that makes it stronger and more resistant to crushing. And for the most extreme conditions, we have ceramic proppants.
Ceramic proppants. That sounds almost futuristic.
It does a bit, doesn't it?
Yeah.
Yeah.
What makes them so special?
They're incredibly strong and can withstand pressures that would crush regular sand. Plus, they often have better conductivity, meaning oil and gas can flow through them more easily.
So it's a trade-off between cost and performance. Natural sand might be the budget-friendly option, but those engineered proppants really step up when the pressure's on.
Exactly. It's about finding the right balance for each specific well. And speaking of finding the right balance, proppant placement is just as crucial as the proppant itself.
That's where the real art of treatment scheduling comes in, right?
Yes.
Making sure those tiny grains end up exactly where they need to be.
Precisely. We've already talked about some placement strategies like perfect support fluids and banking fluids, which use different mechanisms to transport proppant.
Right.
But there are other techniques like using diverting engines that can help fine-tune proppant distribution.
Diverting agents, what exactly are those?
Think of them as traffic cops for proppant.
Oh, okay.
They help ensure the proppant spreads evenly throughout the fracture, preventing it from concentrating in certain areas and leaving other areas unpropped.
That's a great visual. So it's about making sure the entire fracture is propped open effectively, not just certain sections.
Exactly. And the type of diverting agent used depends on the specific well conditions.
Okay.
Some diverting agents create temporary blockages to redirect proppant flow,
Right.
while others work by changing the fluid's viscosity.
It sounds like a constant process of monitoring and adjusting to make sure the proppant is distributed properly. This is getting more complex than I imagined.
It's a complex process for sure, but we've gotten pretty good at it. And it's only getting more sophisticated as technology advances.
How so?
We're now seeing real-time monitoring tools that give us unprecedented insights into what's happening downhole.
Real-time monitoring, so you can actually see where the proppant is going miles below the surface.
In a way, yes.
Wow.
Fiber optic sensing, for example, uses thin cables embedded in the wellbore to transmit data about temperature, pressure, and even acoustic signals, which can help us track proppant movement.
It's like giving the well a high-tech nervous system.
It is pretty amazing.
That's incredible. What other technologies are on the horizon?
Another promising area is radioactive tracer technology.
Okay.
By injecting tiny radioactive particles along with the proppant, we can trace their movement through the fracture using specialized detectors at the surface. It gives us a much clearer picture of how the proppant is distributed.
That's amazing. It's like giving each proppant particle a tiny GPS tracker. With all these advancements, what does the future hold for proppant placement and treatment scheduling as a whole?
The possibilities are exciting. As we gather more data and refine these technologies, we can expect even more precise and efficient proppant placement,
Yeah.
leading to better well performance and ultimately increased production.
That's great news for the industry.
Yeah.
What about the environmental considerations?
Right.
Are these technologies being developed with sustainability in mind?
Absolutely. The industry is very conscious of the environmental impact of hydraulic fracturing and is actively researching and implementing solutions. For example, there's been a big push to develop more environmentally friendly fracturing fluids using recycled water whenever possible and minimizing surface disturbance during operations.
That's encouraging to hear. It seems like the industry is making strides towards more sustainable practices.
Yeah.
Are there any other innovations you're particularly excited about?
One that really stands out is the development of smart proppants.
Oh, profits. Okay.
These are proppants embedded with sensors that can provide real-time data about conditions within the fracture, like pressure and temperature.
So they're like tiny little scientists reporting back from deep underground.
Exactly.
What kind of insights can these smart proppants provide?
Imagine being able to monitor fracture closure over time.
Oh, wow.
This information would be incredibly valuable for optimizing production and ensuring the long-term performance of the well. It could also help us understand how fractures behave in different geological formations.
That's fascinating. It sounds like science fiction is becoming reality in the world of hydraulic fracturing.
It certainly feels that way sometimes. As our understanding of this complex process continues to grow, we can expect even more groundbreaking innovations that will shape the future of energy production.
Welcome back to the deep dive. As we wrap up our exploration of hydraulic fracturing treatment scheduling, I'm struck by how much complexity goes into a process that many people probably never even think about.
It's true. From those carefully designed fluids and proppants to the real-time monitoring techniques, it's a symphony of science engineering and a bit of art too.
Definitely. As we reach the end of our deep dive, what are some key takeaways you hope our listener walks away with?
I think the biggest takeaway is the sheer level of precision involved in hydraulic fracturing. It's not just about pumping fluids and sand down a hole.
Right.
It's a carefully orchestrated process with multiple stages and a multitude of factors to consider, each with its own nuances.
Like we talked about with those perfect support fluids, getting the timing just right so the proppant reaches the fracture tip at the perfect moment. It's fascinating.
Absolutely. And it highlights how much we've learned about the physics of fracturing and how to manipulate those forces to our advantage.
And speaking of manipulation, the TSO technique, where you intentionally create a screen out to widen the fracture, that really blew my mind.
It's a testament to the ingenuity of engineers who turned what was initially seen as a problem into a valuable technique. And it speaks to the importance of constantly learning and adapting in this field.
Right. There's no one-size-fits-all solution. Whether you're choosing fluids, proppants, or placement techniques, it's all about understanding the specific challenges of each formation and tailoring the approach accordingly.
Exactly. It's about finding the right balance between cost and performance efficiency and environmental impact.
And it seems like those considerations are becoming increasingly intertwined. We talked about the push for more sustainable practices like using environmentally friendly fluids and reducing surface disturbance. It's encouraging to see those efforts taking shape.
It's definitely a step in the right direction. And with advancements like real-time monitoring and smart proppants, we're gaining even more control and insight into these operations, which can only lead to further improvements in both efficiency and sustainability.
It's incredible to think about the possibilities.
Yeah.
As we wrap up, what's a thought-provoking question our listener can ponder as they continue to explore this fascinating world?
How might the increasing use of artificial intelligence and machine learning impact the future of hydraulic fracturing treatment scheduling?
Ooh, that's a great question. Imagine algorithms analyzing massive data sets, predicting fracture behavior, and even optimizing treatment designs in real time.
Mm.
It could be a game changer for the industry.
It's certainly a tantalizing prospect. As technology continues to evolve, it will be fascinating to see how AI and machine learning further shape the landscape of hydraulic fracturing.
Well, that's an exciting note to end on. We encourage you to delve deeper into the sources we've provided. They're packed with incredible details and insights that will enrich your understanding of this complex and ever-evolving field.
And remember, the world of hydraulic fracturing is constantly changing, so stay curious and keep learning.
Until next time, keep diving deep.